Can I start?
Yes, we're very happy to have Soonwon from MIT talk about quantum thermalization.
Great. Thank you, everyone, for coming and giving me a chance to talk about these results. I have not given a talk about this topic that many times, so maybe my presentation might be slightly rough. So don't hesitate to raise your hand and interrupt me in the middle of the talk and ask any questions. So let's get started. I started at like 2:25, all right? Awesome. Before I start, I would like to make one thing very prominent. This work is done by my students, Saul Platovsky, Camille, who's in this audience room. Where is he? You want to wave your hand? Okay, good. So if you have any questions, you should ask him. He not only has done the technical part, but also like a very conceptual, even the inception of the project. I want to make it very prominent. So let me start by having a super high level discussions, assuming you guys are high school kid, okay? So in modern physics, we have a very two successful theory. One thing, my favorite, is quantum mechanics. It describes microscopic physics, like single atom, two atoms, molecules or ions or photons, how they interact, entanglement, and so on. So we have a fantastic Q-form seminar talk just from Manuel. Okay, here, arguably the most important equation of motion is like Schrödinger's equation of motions. The wave function describes everything about our quantum system. It time evolves under this first order differential equation generated by what's called the Hamiltonian. Second branch of the physics that I like is statistical mechanics. Here, the philosophy is slightly different. We talk about an ensemble of many particles, and we talk about macroscopic scales like total volume, total energy, temperature, pressure. And the systems, due to their collective phenomena, undergo the phase transition. The most famous one is, water melting. The water always melts, like the ice melt into water or like evaporates to gas. This kind of phase transition and thermodynamics, which is literally driving our car, engine, like thermodynamics, is very important. Maybe the most important aspect of this thermodynamics or statistical mechanics is the principle of maximum entropy. If you have a perfectly isolated systems, the entropy system cannot decrease. And in fact, generically, it increases such a way that if you go to a reasonably long time, not so long in practice, it reaches the state that has a maximum entropy and then stay there. So that's the principle of maximum entropy. However, these two branches of physics, if you just look at it naively, have a very serious incompatibility, and there's some contradiction, at least naively, and I'm going to talk about that. So the question is about how the connection arises. To illustrate this, naive contradiction, I want to talk about a thought experiment. Let's imagine we have a perfectly isolated many-body system, quantum mechanical, prepared in a pure audible equilibrium quantum state psi. And we let it evolve under time evolution. It's a generic time evolution, interactions, maybe particle hopping and so on. And they wait for a sufficiently long time and what would be the state of the system at late time. In quantum mechanics, we have a very good prediction. In quantum mechanical theory, of course, the dynamics is generated by Hamiltonian, leading to the unitary evolution. So at any given time, at late time, the wave function will be still pure wave function, but it's dynamic, it always evolves. There's no stopping point, it just keeps changing. If you wait, maybe they'll entangle one another, and then they form a superposition. So it's a very complicated wave function, it's still evolving. This is not the case if you look at the statistical mechanics. It says, after sufficiently long time, the system is described by a single state, a statistical ensemble, that's called the Gibbs state. So generically, at finite temperature, the Gibbs state is a mixed state. It's a probabilistic mixture of many different pure states. And it's equilibrium state, so it doesn't change over time. And this state is literally defined by maximizing, here technically, von Neumann entropy of the state up to conserved quantities, such as like energy in this case. In this entire time, I'm not going to consider any other conservation other than energy. Okay? So in this case, just maximize von Neumann entropy up to the constraint of global energy expectation value. That's going to be the Gibbs state. But there's obvious contradictions. On one hand, we have a pure state. The other hand, we have a mixed state. On one hand, we have a dynamical state. The other hand, we have an equilibrium state, like time-independent state. So what is the resolution? What is the actual solution of our state? So I'm not going to bore you because, or some of you already fall asleep, Yes, the answer is quantum thermalization. We don't demand this entire system to be exactly equal at the global level, but we demand they're equal at the subsystem level. If you look at the subsystem, which is small subsystem A, and look at the reduced density matrix obtained from either quantum mechanical prediction or statistical mechanical prediction, they have to agree with a good prediction, good approximations at all time late time. So this reduced density matrix of the time-dependent state on the left-hand side will look identical over time with very small fluctuations. And this equality leads to other consequences, conceptual consequences, such as entanglement entropy equals the thermal entropy in the pure, the first principle theory. And also, people say the quantum thermalization is essentially the system, isolated system, behaves its own path, such that the rest of the subsystem behaves as a path, leading to the thermalization of subsystems. So that's the idea. So here I talked about thought experiment. This is not really a thought experiment. It's a real world experiment. It's a ubiquitous in the real world. The first one is ultra cold gases. We have highly developed laser technology and control technology so that we can perform experiment that involves many particles interact with one another. They are sufficiently well isolated with the real rest of the universe. So we can with good approximation, they evolve unitarily. Nevertheless, we find them the system which is thermal equilibrium very quickly. The second one is quantum chronodynamics. So if you have a collision of heavy ions with a very high energy, they break into smaller pieces of the fundamental particles, and then they are strongly interacting, described by the quantum chromodynamics. And for a certain duration of time, they form a phase of matter, characterized by this conjecture phase diagram, where the y-axis is the temperature, x-axis is the chemical potentials, and this is considered the hottest matter that could exist on Earth. What it means is it can never be stabilized by the explicit bath, because there's no bath at that temperature. It has to be the quantum thermalization, and this goes by the name QCD thermalization in that community. Second one is black holes. In a certain theory of black holes, quantum thermalization seems to be closely related to the formation of the black holes. I'm not an expert, so I don't want to, and I cannot elaborate the connections, but I'm aware of these connections. Okay, so the key question is how unitary dynamics is compatible with the irreversible falling into the black hole in analogy. And ultimately, our universe, if you believe in quantum mechanics, it should evolve unitarily. So what if the fate of our universe? Does it thermalize as our statistical physics predict, or it does not? It never thermalizes. Okay? Therefore, my thought experiment is not really thought experiment. It's actually real world experiment spanning across almost all branches of physics that we talked about. So in all these systems, quantum thermalization occurs. Do you agree? Who agrees? Right? So as a responsible scientist, can you defend yourself? Okay, right? So what I'm trying to say is quantum thermalization is a belief. It should be, because otherwise we are screwed. We teach in our class statistical physics and quantum mechanics, learning maximum principle, empirical principle, but we don't know whether it's true or not. It's a conjecture, it's a belief. I totally believe it has to be true. I have no doubt it's not true. However, we need to prove it as a responsible scientist. And in fact, there are more practical reasons why we have to prove. The first one is that as a basic physics problem, is quantum mechanical principle and the statistical mechanical principle compatible with one another, and at how much accuracy? And that's a very basic science question we want to understand. Unitary evolution. I have a dedicated slide for the classical systems.
This objection keeps even harder to talk about.
Yes, to give you the trailer, I'm arguing because of our proof, we are going to present the proof for a certain class. Quantum and classical are fundamentally different. And the physical conditions, so we know over the past decades, due to many of the pioneers, some of them in this room, we have a good understanding that there could be robust violations like localization, or maybe many-body localization, many-body scars, integrability, Hilbert space fragmentations. There are different mechanisms of violating quantum thermalizations. By having a rigorous proof, we can show under what conditions it can be violated and cannot be violated. Okay? The third one is maybe we have a better understanding, as Vedika pointed out, is there any unique features that are coming from the quantum mechanics distinct from the classical physics? So we have a better insight about the mechanism of thermalization. And that's the point of making a proof. So indeed, there has been many approaches, not just proving, but probing quantum thermalization. So it's a heavy literature, almost like a field. So I don't want to review them. It's just too gigantic, but I just review by like maybe one sentence per each. The first approach is numerical simulations. We literally simulate quantum mechanical dynamics using our computer and then see whether local subsystems look like thermal or not. Or we can perform quantum simulations or quantum experiments, and we perform experimentally probe quantum thermalization. Like it's a topic was taught in QFAM seminar. Or we have very meaningful empirical conjecture with the hypothesis. The most famous one is the eigenstate thermalization hypothesis. It's not hypothesis, it's a hypothesis, not proven. However, it gives us strong predictive power to make a predictions and then quantitative calculation of what the system should have happened. Okay. And also more recently, we have observations such as what's now is called the deep thermalization. Maybe the thermalization is not the end of the story. There's a bigger picture there. But in today, I'm going to talk about a rigorous approach. And there are past few decades, there's been like several different ways of approaching the problem. One is coming up with the exactly solvable toy models as a representative. Maybe you have heard about exact calculation of spectral form factor or dual unitary dynamics. Or we use better statistical or information theory tools, especially the quantum information theory tools, to prove the rigorous bounds about how the system has to thermalize. And the last part is going to be the approach that we take in this project. So without further delay, I'm going to tell you our main results. So we ended up proved quantum thermalization must occur for a large class of quantum systems, not all classes of quantum systems, but for a large class of systems and large class of conditions. Specifically, the conditions we consider is all qubit Hamiltonian described by local interactions, geometric local interactions with the three added conditions. One is translation-invariant Hamiltonian. We imagine qubits arranged in either 1D, 2D, or 3D, or arbitrary dimension, finite dimensions, regularly spaced. Each term in the Hamiltonian is acting on some finite range, and the same form is repeated over different position. Second one is, as we will elaborate further, we'll talk mostly about high effective temperature. We'll talk about ensemble of initial state, where the average expectation value of energy of the initial state such that it corresponds to high effective temperature. And finally, we make a technical assumption that called the no perfect resonancy spectrum, or like more the technical terms, non-degenerate spectral gaps. Maybe the third condition is less familiar to some of you. So let me elaborate what it is. The non-degenerate spectral condition is this. It's a property of the Hamiltonian and its eigenvalues. Suppose I'm given a Hamiltonian for a finite size system. So it's a finite dimensional Hilbert space. Suppose I diagonalize it and obtain all the energy eigenvalues Ej. And now we pick a pair Ij and compute their energy difference. That's what I call delta Ij. I say the Hamiltonian has non-degenerate spectral gaps if for every pair Ij, where I not equal to J, they are distinct from one another. So the only way that the energy gaps match is when they are equal to one another. Okay, and this condition implies there shouldn't be a degeneracy, because if there's a degeneracy, we can choose a pair such a way that they are resonant one another. We demand that this is not true. As long as this is not exactly true, we can talk about thermalization for infinite time limit. Any questions so far? Okay. So this is a statement again. So under these three conditions, translation invariance, high effective temperature, and no resonance condition. No resonance condition is just difficult to check. However, there are some promising results, such as, in fact, if you consider generic local Hamiltonian without translation symmetry, then without translation symmetry imposed, then, except for the measure 0 point, you can show that the no degenerate spectral gap condition is satisfied. In other words, this is violated only for very fine-tuned case. Corresponding statement, when you have an added symmetry constraint from the translation symmetry is widely believed but has not been proven. But there are some progress, and if you're interested in, please talk to like Saul. No, I demand this across all momentums, but it doesn't change the generality too much. Yeah. Yes.
There's some intuition to why
with the imposed translation symmetry. Because why? Because like it's matching exactly the same thing for the eigenvalues, right? There must be some kind of fine tuning, right? So this is basically a solution of our polynomial equations, right? And then their relations. Why do that be like perfectly the same? Translation symmetry is an abelian symmetry. Therefore, we can divide into different subsectors. Other than that, there should be no correlation among the eigenvalues. There'll be no repulsion among the eigenvalues because they are different symmetry sectors, but they don't have to be they don't have to be coincide. So there's no so they actually being equal would be very surprising. Did I answer your question? Yeah.
Can you talk a little more about what types of Hamiltonians do not satisfy this? So like, does a type clock Hamiltonian probably have the degenerate spectrum?
Oh, so we are talking about infinite, the kind of like a bulk of the spectrum. So type Hamiltonian, I'm not sure whether it's special at all. And also we demanded translation invariance, so that's another translation. For the not this condition, but this condition is what we assume, right? Yeah, that's right. Yeah, that's right. Yeah, any stabilizer, any integrable system that we know of violates, like free fermion Hamiltonian violates this condition, so it shouldn't thermalize. Beta on such integrable system, everything that we know of has an inversion symmetry leading to non-abelian symmetry, leading to degeneracy and violated symmetry. So like as far as I know, almost all examples where it shouldn't thermalize does not satisfy these conditions. Yes. Absolutely. 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 So at the same time, we were not able to prove a thermalization for system that has extra symmetry if the symmetry is non-abelian, including the inversion symmetry. Mm-hmm. Yes, Vedika. Yeah. Local thermalizations. Yeah, it involves more than proving dephasing, but what you imagine is right. Like local indistinguishability of thermal state or the initial state time evolved if the initial state is chosen from ensemble with high probability. Okay. Yes. This is stronger than non-degeneracy. This implies non-degeneracy and more. Yeah. Good. Good. More questions? Yes. Yeah. So we can just second order. We don't care about higher order. Yep. Okay. Any other questions? Okay. Then before going to talk about the proof, let's be a little sharper about what we mean by quantum thermalization. So it'll be slightly more technical than what I have done so far. Okay. So quantum thermalization is a local equivalence between time-evolved pure state and thermal state. So what do I mean? So let me consider a physical initial state. I want to be concrete about what I mean by physical. Yeah. Yeah. That's a single particle orbitals, not the. Yeah. Then first of all, we talk about the spins only. So it's already different. But morally speaking, it's not a fundamental obstruction. It just means it's delocalized. In the single particle picture, it just means it's delocalized over space. Once you add on the interaction issue. Hofstadter butterfly, the single particle orbital. If you have interactions, then it should, yeah, exactly. Yeah, at high temperature, yes. Okay, good. Okay, so here we consider unentangled pure state. Edwin gave a fantastic talk about what he means by unentanglement. So like, thank you for that. So in other words, like, but we consider pure state is literally a product state, a tensor product of state where individual qubit is in some direction in the the phase space, and that tensor product I just say psi 0. We consider time evolution under some given Hamiltonian, and then consider time of state psi. And we are going to consider the reduced density matrix obtained from here. It depends on the initial state and of course the time in principle. On the other hand, we are going to talk about gift state. This state is e to the minus beta h. You can understand it as a max entropy state up to energy conservation. So if you choose beta such a way that expectation value of energy of this beta state matches with our initial expectation value of energy, and that's what I call as E beta. So every beta about total energy E beta. And then again, calculate the reduced density matrix. And the statement is this rho A psi and rho A beta should be almost equal to one another almost all time when time is sufficiently large. Okay, that implies that this is not changing over time too much. And to be more precise, we just say they are approximate to one another in terms of observables. Let's consider the expectation value of observable supported in A. I assume the observable has a finite strength normalized, and then compute the expectation value difference, and then try to choose the optimum observable that make as distinct as possible. So you just take the absolute value and optimize over A. So that's like largest distinction we could potentially have for any observable within support A. And I define that as this expression, which in jargon is called a local trace norm. Just simply a trace distance of these two operators. And we want to say this quantity is small or goes to 0 at typical late time t. How do we say this is true for a typical late time t? I just compute the average over time t and show that it goes to 0. And you are going to claim, hey, like average, on average 0, maybe it'll be non-zero at some point. That doesn't happen because what's being averaged is always non-negative. So if the average is 0, the only way is there's no cancellation. It has to be almost everywhere 0. So notice that this is different from the fact that we demand time average state is indistinguishable from the gift state. We said every time t they have been indistinguishable because on average it's time t. And also this does not mean it's true for all time t, but almost like many large portion like typical time. So I didn't put you like explicit bound, but it'll be in some thermodynamic limit. It'll be like basically like probability 1. Okay. So what we want to prove technically is this quantity. What we want to show. We had good starting point, except that we just learned that this is an undecidable problem. So very recently in 2021, there's a nice paper basically proving the following statement. For a given unentangled initial state psi and Hamiltonian, even actually restrict to the translation-invariant Hamiltonian, it is computationally undecidable to determine whether the psi thermalizes under H at infinite time or not. So what it means by undecidable is, this is a quote from the last sentence of the abstract. No general theorem, algorithm, or systematic procedure determining the presence or absence of thermalization in any given Hamiltonian. So that's rigorously proven in this paper. Therefore, we shouldn't attempt to prove this because then we are just wasting our time. Even though we add more assumptions like non-degenerate gap conditions, we can generally expect that, okay, proving this statement is very hard. So instead of proving exactly what I just said, I'm going to prove in a slightly different way. And that's what we call the typical state thermalization. So instead of considering a particular initial state and a Hamiltonian, I fix Hamiltonian, but instead have an ensemble of initial state. So let's consider a set of pure product states, psi 1, psi 2, psi 3, they're all product states, and they associate with some probabilities forming an ensemble. Okay. Imagine picking a state from this ensemble, from this ensemble, and then we are going to show that thermalization of this particular state with high probability, and we say this is true for high probability. Okay. This way, we avoid this no-go theorem because we have not given a particular state in the Hamiltonian, but rather have a typical state. Okay. It turns out this approach works. Yes.
You demand that initial state to be translation invariant?
No, we do not demand the initial state translation invariant.
You demand that your initial state, not be a superposition over too many entities. if I took a coherent version for the whole eigenstate line, but
So I'm going to talk about what this ensemble has to be. Okay, so for now, it's considered as a general pure product state. Okay, but of course, this statement is meaningful if this ensemble is very large. Okay, if I define the ensemble to be the ensemble of initial state such that it thermalizes, of course, it's obviously true, right? So we want this ensemble to be somewhat independent of whether it has to thermalize or not, but more physically meaningful. Okay, so we just introduce a notion, like quote unquote, like a large ensemble. So we define typical quantum thermalization so that this quantity averaged over time and average of the choice of initial state all goes to 0 in the proper thermodynamic limit. Again, this averaging is outside the norm, so this being goes to 0 means like everything goes to 0. For the large ensemble epsilon, so epsilon cannot be arbitrary epsilon, we want to choose it to be largest ensemble in some physical sense. So what we demand is, let's consider all different kinds of ensembles of pure product state, okay? And for each of them, we compute the average state. So this is an average of the state. And we demand that von Neumann entropy of that average state up to energy constraint is maximizing its entropy, okay? So, and by the way, I forgot to mention, like this ensemble has already fixed beta. So like we are talking about thermalization of given temperature in the rest of the part. Okay. Yeah, these are all product states. Consider all different ways of choosing set of pure product state and their distributions in a way that their average state maximizes their entropy, von Neumann entropy. Okay, the solution is not unique. There are different ways of forming the same average state, but different unraveling of pure product state, infinite of them. Any ensemble tree is okay. For each of them, we will going to prove thermalization. Yes. Yes, turns out that's non-trivial because if you choose optimization over the entropy for the energy constraint, without constraint of being your product state, they will be the gift state. Here we have an extra constraint that the constituent of state has to be product state, right? So unless the global state is separable, this optimum will not be the thermal state. But turns out we'll leverage like Evin's results in the last part of the talk. So for the temperature that's relevant to our, and partly that's the responsible portion of why we talk about high temperature. There it'll be same as the gift state. Yes. Oh, so this being 0 will be bounded by like decreasing function of total system size, and subsystem size should be independent of the total system size. So any finite constant size, or if any finite size in thermodynamic limit. Okay.
So you can make nodes on the variance of H in any of the states in your column.
We'll prove that. We do not demand it. We'll prove that. Yes. Actually, that's not the hard part. That's very easy to prove, and that's not us. Yeah. It has been proven, yes. Any other ones? Okay, cool. So recap, the more technical, like informal version of the theorem is this. For any n-qubit system in d dimension described by the Hamiltonian, the system exhibits a typical quantum thermalization as I described in the 3 conditions: translation invariance, non-degenerate spectral gap, and that the temperature of the ensemble we talked about is beyond a certain threshold temperature T star. That's independent of system size. And technical formula is this local trace norm, averaged over time, average over psi, is vanishing function in the limit n goes to infinity for any positive value delta. Okay, so let's take a talk about the example. The temperature T equals to infinity or beta goes to 0. So for example, let's consider translation invariant Hamiltonian, and we have to assume it has a non-degenerate spectral gap. Then we consider ensemble of pure product state. Here, a particular, say, product state is like V1 for the first qubit, V2 for the second qubit, and so on. We can consider different types of ensemble. First ensemble is individual qubit state is drawn IID random, independently random, either 0 or 1. It's a classical D-string configurations. And that ensemble, the first ensemble, will consist of like 2 to the n configurations. Second ensemble is this state will be one of the 6 points, the bottom of, x minus x, y minus y, like the stabilizer states, or just random from the block sphere, uniformly random, independently from every site. For all 3 ensembles, if you compute the average state, rho epsilon, for each case, That's rho max, maximally mixed, which is infinite temperature Gibbs state. Therefore, it constitutes our definition of large ensemble. Okay? It maximizes entropy. Energy constraint doesn't do it too much at this level. So E epsilon beta is a large ensemble. Therefore, our theorem implies that if you choose random, typically choosing bit string 0, 1s, it'll thermalize to locally maximally mixed state as sufficiently large. So our result implies entanglement development. Or random stabilizer state will thermalize. Random product state over continuous space will also thermalize. I have to mention that the second and third results has been already proven by Chen and Aram several years ago in this particular paper. I think this particular paper needs more, attention. So please read this paper. This first thing, the B string result is somewhat stronger results because even when the system is completely classical under quantum Hamiltonian with non-degenerate gap conditions, we prove quantum thermalization. So it's a more restricted set, but we were able to prove thermalization. The corresponding statement for finite temperature beyond our threshold should look different. We just talked about random product state thermalizing to infinite temperature. It's understandable. If you have an independently random uniform product state, total energy will be basically on average the middle of the spectrum. So it has to thermalize to infinite temperature. So in order to talk about finite temperature, we have to talk about some initial state ensemble where they have a certain level of structure. At least expected energy density should not be at the value of infinite temperature. It should be some finite, correspond to the finite temperature. Okay, and that's why we need to impose extra conditions about the choice of initial ensemble. In this talk, we choose by maximizing the von Neumann entropy of average state. And as I already mentioned, for the relevant temperature, that will coincide with the Gibbs state. Okay, so let's talk about implications. So what does it imply? One of the most important implication is you guys can sleep better now. As a responsible scientist, either in physics or computer science, I know just like me, you had many nights where you stay awake until late, wondering about, what if quantum mech and stem mech are not consistent with one another? No longer have to do that. At least for a certain class of systems, we were able to prove that the system thermalizes. So hopefully today, if you go to a hotel or your room, okay, you can sleep very well. So that's maybe most important, implications. Except that maybe starting from tomorrow, you should start thinking about the other regimes, the low temperature, fermions, like infinite space-time dimensions. So let's do it together. Okay. But more on a serious side, the implication is that our work conceptually implies that statistical physics is an intrinsic emergent phenomena that we can derive from quantum many-body physics, the quantum mechanical principles. And maybe this is like overly stated, except that maybe we'll be surprised this is not the case in the classical system. So in order to contrast, let me talk about the classical system for the next 2 minutes. Okay? Yes? I haven't sketched how to prove, but I'll get to that in the later part. Okay. So let's talk about the classical system. So what's relevant to classical mechanism is classical chaos. So our state is described by the point in our phase space, like position and momentum generalized versions. And we know if you have two initial points close to one another, over time, they depart from one another at an exponentially fast rate where the exponent is called the Lyapunov exponent. Okay. Therefore, at the late time, within very short time, a log of the volume of the phase space volume, it reaches essentially random. Okay. But actually, that's not true. Because if you have a single point, the entropy associated with the system is 0. And that entropy is still 0 if you evolve for a long time because it's a single point. So there's no entropy to talk about here. So we need to impose a little bit of uncertainty in the initial state, which is valid because we can never measure any phase space point with the perfect precision and due to human capability. Okay. So this is where in the classical system, information theory enters. We have a bounded ability to measure something. So let's impose uncertainty by hand because I'm not knowledgeable of that state. So that's the information theory. And then talk about time evolution. Okay, now it makes sense. Under Master's equation, this distribution deforms, and then you have different distributions and different distributions, except that they are all equal to one another. The entropy does not increase. Because Hamiltonian's flow is incompressible flow, therefore, this does not have different entropy if you just calculate exactly. Okay? So there's no entropy production, even if you have an entropy in the initial state. Yes? That's right. We'll get to that. Yeah. Next slide. But suppose your knowledge about your ability to perform measurement at the later time is limited, either because you measure subsystem or because your resolution is finite. What's now relevant is the entropy of this phase space volume, but what is the discrete value that we could have obtained? So you divide the phase space into smaller grid and count which boxes has been touched by these distributions. The number of boxes in this plot grows exponentially. So if you define the entropy by log of the number of boxes, that linearly grows, and turns out so-called due to so-called the passing theorem, the rate of entropy growth defined in this way is exactly equal to sum of the Lyapunov exponent. Okay. So the take-home message is max entropy principle in the classical system requires uncertainty both in the initial knowledge of the state and our ability to perform measurement. And this inability is not intrinsic to the dynamics, it's our interface, the human knowledge, which is not the case in the quantum because we just showed. Okay. From that point of view, our implication is that there are some fundamental distinction between quantum and classical when it comes to statistical physics. And third, yeah, go ahead.
But in the quantum case, you also constrain the super subsystem. So why? I mean, at least why you're making this distinction?
Oh no, that's right. In the quantum case, locality and entanglement draws a thermalization. The locality is important, of course. Yes. That's right. But how about the initial state?
I would say that like you're using some ensemble, right? Like I could probably do the same thing.
No, I didn't say initial state. I don't consider ensemble. I consider ensemble to prove the statement, but the statement is about individual pure product state. And pure state has zero entropy globally. I agree with you. So locality and the restricting to the locality is necessary in the quantum case, because otherwise we know the statement is not true. Quantum mech and state mech are different without locality because globally pure versus globally mixed. So that's inevitable point, right? But in the classical case, we need to impose this ability, extra ability by hand, inability knowing the initial state with the perfect precision. Okay. All right. The third implication I just go mention very quickly, and I'm not sure that's like it's a serious implications, which is, if our goal is to prepare the Gibbs state, but not really perfect Gibbs state, but something that's locally indistinguishable from the Gibbs state, it is sufficient that you choose a suitable product state and then time evolve. This kind of statement has been assumed in many of the condensed matter or like out of equilibrium, physics communities, but you can sleep very well because at least on a high enough temperature, we prove the statement. Extra knowledge is that this is fully unitary and therefore reversible. So this is particularly useful if you plug in this state as a subroutine of bigger algorithm, which is not necessarily the true in the state-of-the-art algorithm to prepare the Gibbs state, because they are relying on the open system dynamics. You cannot, it's not clear to me how to use that in the subroutine. And also here, there's no ancillary qubits other than the rest of the system, which is math. So it's nice. On the other hand, our error bound is not so good. It's only polynomial in global system size, while the subsystem size is small. And also, as I said, we don't talk anything about how fast it thermalizes, so we have to wait infinitely a long time. But my understanding is even in the state-of-the-art algorithm for preparing the Gibbs state, a time bound is actually like a bit difficult, but maybe I should stop. I should stop talking about it because I don't know the state-of-the-art algorithm, in a fair fashion. Okay, any questions so far? Good. Remaining time, yeah.
I thought when you were contrasting with the classical system, you might have pointed to another part of the classical language, KAM. So if I understand the result of your thing, you're sort of saying that you have to really fine tune to get a system that does it for you.
That's a good point. You're right.
Classical system, there is a distinct result. If you take an integral system, there's an open set of Hamiltonians, at least the finite number of degrees of freedom around it.
I put that in my future slides. Yeah. So let me just for everyone. So in the classical chaotic system, if you have a non-thermalizing or integrable system, even if you add a small perturbation, it remains non-thermalizing. But what we showed is, assuming this non-degenerate gap condition is like only true for measure 0 point, an integrable system, if you add a perturbation, it has to thermalize at least at infinite time. So therefore, this robustness does not exist if you formulate in this way. So thank you for pointing that. Yeah. Okay. Yeah.
Like extended Hamiltonian lattices bound from the AM theory. Like the bound on like the measure of regular because of the infinite number. In this context, like there's no. Right. But if you still, if H bar goes to zero, you have a lot of cells. You don't have a lot of disease. You have a lot of quantum states. Right. So
Yeah.
That's exactly.
Maybe we could talk about the discussion like after. But I agree to see the point. It's about the how fast it goes to zero in our proof. It's 1 over square root of n. But we can talk about that. Okay. So for the remaining time, I'll just sketch how we ended up proving it. So of course the details is it's hard to deliver in a finite time. It's a restricted time. So we present a flow diagram of our logic. So this is not meant to be understood in full detail in a single slide, but we are not reinventing the whole thing from the scratch. We are building on top of many existing and seminal results. So the color scheme is not as good, but the blue one is our results, and this pink one is assumptions, and the green ones are known results. So I have an interdependence, and some of them is this, what Ewan just talked about, the separability of given states. And if you want to learn about the details of this, like Saul is the perfect person to talk about this. But for the remaining time, I'll just sketch like high-level picture of what are the overall, logical flow we make. So to prove thermalization, we want to show local indistinguishability for different choice of initial state, averaged over time and averaged over initial state by just skip that notation. To do that, we introduce time averaged state. So this goes by name of diagonal ensemble. So it's a mixed state obtained by averaging that initial state time evolution over infinite time. Use this as a ladder to establish this, namely, we are going to prove what's called the equilibration. The initial state is locally indistinguishable to this diagonal state for each initial state for majority of the time and late time. Okay? So it basically doesn't change over time too much. It just without small fluctuations. Okay, so that's the equilibration. And then we are going to show this diagonal state and then given state are actually locally indistinguishable. And by simply putting them together using triangles inequality, we'll show this pivot state and the given state are locally indistinguishable. Everything on average on the typical set. So this equilibration is turns out not so difficult to prove. So equilibration, the idea is borrowed from this paper. So there's a theorem. If the spectrum of Hamiltonian has non-degenerate spectral gaps, and somehow if you can show that initial state is a superposition of many energy eigenstates of Hamiltonian without having to compute Hamiltonian, quantified by this inverse participation ratio. So it's a population square and summed over. So this measures effectively inverse of number of states comprising our initial state. If you show this initial state has a small or vanishingly small IPR, together you can show this equilibration. And this is the formula. This average quantity is bounded by IPR, which will vanish and it goes to infinity limit. Okay. This theorem is easy to understand because let's write down this state in the energy eigenbasis. There's a diagonal terms that defines diagonal ensemble and off diagonal terms. But this non-degenerate gap condition means these off-diagonal terms oscillate all at distinct frequency, like all these incommensurate distinct frequencies. I don't know incommensurate, but it's all distinct frequencies. And then the fact that you have a vanishing IPR means there are so many psi ij that contribute, and they have to be necessarily small. So there are so many terms at the different frequency oscillating. So intuitively, it makes sense. Okay, their average behavior will be whatever the mean with the suppressed fluctuations. It's just kind of law of large number type arguments. Okay, so that's how the equilibration works. So it remains to show the IPR for the typical initial state decays as in the thermodynamic limit. And we do that by leveraging translation invariance. So the idea is here. So let's present a simplified version. Let's say the computational base state where the bit strings is 0 and 1s in 1D, uniformly distributed. Our strategy is we consider two sets, which is periodic set where we translate and it comes back, or aperiodic set where only when you rotate n times it comes back to the original configurations. And turns out among the 2 to the n, only the majority of them is like this aperiodic, and the exponentially small fraction is atypical. Okay, so we are going to just ignore the periodic one because we are going to make a typical statement. For the aperiodic one, let's talk about overlap with the energy eigenstate. But because there's no degeneracy and Hamiltonian is translation invariant, eigenstate is also translation invariant. Therefore, you can act on this translation operator to the right and argue that overlap is the same for the different configuration and different configurations. Okay? That already tells you that the population of a particular configuration in energy eigenstate has to be at least 1, and mostly 1 over n. Okay? And that gives you the inverse participation ratio that has to decay with 1 over n. Okay? And turns out we can generalize statement for the broader class of ensemble of initial states, namely, so this is theorem 3, informal version, as long as average state of the ensemble has a finite correlation length. For the translation invariant Hamiltonian, this is true. And this finite correlation length is proven for high temperatures. Okay. And in order to do that, the proof technique we relies on, okay, like if you translate them, maybe they still have overlap to solve, but we have a notion of approximate periodic, state. So, that's how it is here. So please ask him tough questions. Okay. So we are done, half done, like equilibration. So we want to prove the equilibration, equivalence, which is harder. Yeah. Absolutely. Actually, there are even other works where we use slightly different initial state ensemble. IPR can be known to be exponentially small. And we totally believe the IPR is exponentially small. And that's right. But turns out improving further, this doesn't give us tighter thermalization results because it'll be bottlenecked by equivalence anyway. Okay, good. So let's talk about equivalence. How do we show that time average state is equal to the given state for the typical initial state? We combine 3 different ideas: decaying correlation, weak ETH, and separability. People say, oh, weak ETH is a hypothesis. No, it's a rigorous theorem. I'm going to explain what it is. The first and third one depends on the high temperature conditions, and second one depends on decaying correlation and translation invariance. So decaying correlation is a concept that if you consider 2 observables that are sufficiently far away, their connected component of the correlation has to decay exponentially. And the length scale psi is a correlation length. So if you have a finite correlation length, that means over long distance in the thermodynamic limit, there will be basically negligible correlations. And it has been proven that for any reasonably local Hamiltonian, if you go to sufficiently high temperature beyond a certain threshold, independent of system size, all given state behaves, have an exhibited decaying correlation. And our temperature will be always higher than this threshold. And this is another temperature that sets our threshold temperature. The weak ETH is a very important seminal result originally proved by Murray. Here we made a variant of it so that it's better suitable and in some sense a bit stronger for the high dimensional case. The statement is this: if you consider the probabilistic mixture of energy eigenstates of translation invariant Hamiltonian, local Hamiltonian. Okay, so we consider any mixed state, you say rho d. If somehow we can show rho d has a decaying correlations like thermal state, then for all observables, the local expectation value for energy eigenstates or given state, the averaged version, has small variance for the typical choice of eigenstates. Okay, so this is a weaker version of energy, the ETH in 2 senses. A, the size of the observable is a constant, and B, this is a probabilistic statement. In fact, a lot of heavy lifting goes into the assumption that rho d has to be decaying, has to exhibit a decaying correlations. Okay, so what's non-trivial is if I hand you non-equilibrium product state, consider diagonal ensemble of that, like time average version. How do you show that state has a decaying correlation? Actually, we don't know how to show it, so we'll circumvent that constructions in our proof. The third result is what Evan talked about for the past hour, so I'm not going to elaborate. It turns out very recently, earlier this year, we showed that any Gibbs state at sufficiently high temperature can be considered a mixture of the product state, and not only product state, like a stabilizer state, one of the 6 cases. Okay, and that's remarkable. And for our purposes, what it means is, if you consider all set of ensembles of pure product state and try to maximize the von Neumann entropy of their energy, that constraint is lifted because this ensemble choice, you can choose it to be this particular ensemble such a way that our von Neumann entropy matches the von Neumann entropy with the unconstrained optimization, which will be just thermal state. So this implies any product state ensemble with the maximum von Neumann entropy is equal to the Gibbs state. And that's a crucial element that we leverage out of these results. Okay. But as I said, with the infinite temperature case, this ensemble need not be this form, it can be anything. But we show the existence of this ensemble. So that's the important part. Okay. Okay, so combining this decaying correlation, weak ETH, and separability leading to equivalence, I'm going to present the proof. It's actually 4 lines. So in some sense, our creative work can be all condensed into these 4 lines of the results. But first of all, we want to show diagonal state is locally distinguishable on average for the initial state. What we are going to do is, using non-degenerate gap condition and non-degeneracy conditions, we first rewrite this diagonal state by writing in the energy eigenbasis. And this is a population of individual energy eigenstates. And this is just a resolution of identity. Okay? So this is from the definition. What we are going to do is, but we have to average over this choice of initial set outside this norm. Okay? But what we are going to do is we switch the order of summation over J and this norm absolute value. So that's an expensive operations. We lose a lot of the the tightness, but we just do it. This is just triangle inequality. So instead of adding them up and then average, we just take the average, the absolute value, and then add them up, the triangle inequality. But what enables us is successfully we put the psi outside of the norm. Now we can perform averaging over state. And now using the separability results at high temperature, we show that all ensemble that, that large ensemble we define, the psi averages to GB. So we have this quality. Okay. So this formula is what's very similar to the results in the weak ETH, where we assume this eigenstate is actually drawn from a thermal state. So this exchange is kind of the crucial point, even though it's mathematically simple. That allows us to use weak ETH, and then we show this is bounded. This way, we show that the time average state, basically the equivalence of the 2 ensembles. So we given the equilibration and equivalence, we prove the thermalization for the typical case. So I think I have a sufficient time, so let me pause and get any questions.
Could
Yes.
you go back to that slide?
Yep.
In the third line,
Yep.
I thought that was the definition of the large ensemble. The expectation value over psi is data.
Yeah, so I take definition being the following: consider ensemble of pure product state, and maximize the von Neumann entropy of average state. Okay, that state need not be a thermal state at the low temperature. That's right. But at high temperature, they'll coincide with the thermal state. Yeah. Yes. That's right. That's right.
Both which you have to be higher than?
Yeah.
How do those scale with system size, or are those just sort of fixed temperatures no matter what system size
T
is?
correlation and T separable are both system size independent order 1 quantity. Exact value can be bounded by like strength of the Hamiltonian terms and then degree of connectivity and so on. We have to choose whatever the larger one. Any other question? So that's how we prove quantum thermalization. And turns out this was my last slide. So we have a future directions. So we want to prove quantum thermalization of ensembles defined for the lower temperature, where the Gibbs state is maybe not separable. We believe this is doable, but we are debating about what's the meaning of this, or what's the meaning of the thermalization when the initial state ensemble is not a product state ensemble. But I'm happy to have a discussions. But I want to mention that our definition of thermalization based on product state cannot work below a certain low temperature. Here, roughly speaking, we are making a kind of canonical statement. As long as certain conditions are satisfied, no matter the details of the Hamiltonian, I guarantee you it thermalizes in a typical sense, right? But if you choose the adversarial situation, like worst case situations, there might be some system where low temperature can never be achieved with the product state. For example, frustration state, if you try to minimize energy over all possible initial product state, you cannot reach the ground state. In fact, you cannot reach the lowest energy density. That means the energy density below a certain temperature can never be achieved by any product state, and we cannot talk about thermalization formulated as a product state evolution. So there's a certain fundamental limit about lowering the temperature if you formulate thermalization with product state. And incorporating the symmetries, like even the simplest symmetries, like invergent, especially emergent symmetry, prevent us making any rigorous statements. However, in that case, we understand why the degeneracies are rising. So maybe we just divide into several sets and then talk about different sectors separately and handle this massive number of non-degenerate gap conditions in a smart way, and then maybe it's okay. So I'm wishful about handling symmetries and then generalized Gibbs ensembles. And finally, we are entering the realm of talking about fundamental physics, because it's about proving stuff. For that, we'd be interested to know about generalization to the non-qubit systems, especially bosonic systems or the field theory descriptions, where there are fundamentally distinct ingredients that we need to handle. So with that, let me finish my talk. Thank you so much. I hope you have a good sleep tonight.
Regarding this last point about the product states, could you consider the ensemble of states that is just e to the minus beta h over 2 times product states?
That you're already on average somewhere.
Sorry?
Okay,
those
I
are not
misspoke.
thermalized.
Yeah, you're right. You're right.
And
okay,
they definitely have the property that the average is exactly equal to the thermal density matrix.
Yeah. In fact, actually, we are almost done. So it's a good point. So glad that you asked. I presented the main results, but we have a more technical result. If you see here, we have a so-called Etch theorem. The theorem goes as follows. You consider local translation-invariant Hamiltonian with non-degenerate gap conditions. If you consider an ensemble of pure state, not product state, but ensemble pure state, so that A, individual constituent state is delocalized energy. So IPR is small. And their average is thermal state. So the ensemble you describe is very likely to be an edge state, except we need to prove delocalization of energy, which is, I think, is doable. Okay, but we haven't done it yet. Those states thermalizes in the typical sense. So we have this proven these more general conditions. So in some sense, if you relax the initial state being product state, we have a more general condition. So average triangle. So the H means energy delocalized Gibbs ensemble. So individual state has to be delocalized energy basis, and it has to average to the Gibbs ensemble. Then we can show thermalization. Okay. Yeah.
I just want to double check again with the integrable systems. So with beta ansatz integrable systems, you get this tower of conserved charges.
Yeah.
And then any linear combination of the charges will still be integrable.
Yeah.
And then the higher charges often break symmetries of the lower charges.
Yeah.
For example, you can explicitly break reflection symmetry.
I didn't know that, but yeah, probably yes, yeah.
And then, so I suspect there should be beta ansatz integrable systems that don't have reflection symmetry because of that.
Can you give me an example? Because we haven't found one.
Either XXZ in doing a linear combination of the first two charges. So the usual XXZ Hamiltonian plus the next higher conserved charge. If that fails, then the XYZ integrable
So
model.
how would you, here the inversion symmetry, the spatial inversion symmetry I'm talking about.
That's right, and that's what I'm breaking.
But all integrals of motions in this best unsolvable model is translation invariant with inversion symmetry.
They are not with inversion symmetry. For example, the Heisenberg model, the second charge is S dot S cross S. It's a scalar triple product, and it's inversion antisymmetric.
Interesting, yeah. But maybe there's another mechanism of breaking.
And for Heisenberg, it will, because it will turn out that's actually symmetric under spin flip and inversion.
Yeah.
And so then it won't commute with translation.
I see.
But I think for XXZ or XYZ, I think you might be able to break all non-abelian symmetries.
Okay, that's very interesting to know.
And would you expect it would thermalize in this sense?
Yeah, because
Okay.
initial state will be typically populate all different other generalized ensembles in a different way. But we can actually generalize this. Maybe in that system, I'm speculating here. If you, maybe we can, like as Jungwon said, we can define the separability in a more refined way. So you define the generalized Gibbs ensemble for the different chemical potentials, and then show the separability in that sense, define in the individual sectors. I don't know how to do, but maybe we can do that. And then we can summarize to the all generalized ensemble in that way. That's I.
But here I'm wondering if maybe you can actually just thermalize to e to the minus beta h.
Yeah, I think so.
Yeah,
It
sounds
has
good.
to be. You're right.
Thank you.
So you were, if I understood your definitions correctly, you were saying before that Hamiltonians where there are no low energy states which are product states do not thermalize according to your definition.
No, I'm saying like attempting to prove thermalization of initial product state at all temperature might be doomed because energy is conserved. You cannot reach substantially low and no temperature.
Sure, I see.
Okay.
Yeah, I guess I was wondering if there are any connections between this and like the NLTS conjecture and Hamiltonian complexity, where, like, could you like, okay, if you think NLTS Hamiltonians which don't have simple product ground states, if you can show they don't thermalize according to your definition, does that imply that they can't meet all the criteria? Like you say, you can't make an NLTS Hamiltonian with non-degenerate spectral differences, or is there any connection there?
That's an interesting thing, but in our talk, we only talk about translation invariant and geometric
I see.
locality. So it's already like ruled out.
I see. Oh, I see. Okay,
Right,
that makes sense. Cool, thanks.
So yeah.
Well, we can continue the discussion over coffee. Yeah, thanks a lot.
Thank you.